Okay, we spent a lot of time looking at polynomials, linear functions, quadratics, all those sorts of things, but there's other very special functions we need to look at. So the next few topics, we're just going to be looking at specific types of functions, which will then allow us to really use the calculus to do some good practical sort of questions. So the first one of these special functions is the logarithm function. Logarithms are the inverse of exponentials, or exponentials are the inverse of logarithms, depending on which way you want to look at it. So basically, here's how we work out a logarithm. We are more familiar with exponentials, I suppose. So if y is equal to a to some power of x, if I want to make x the subject, well, to undo the exponent, if you like, we log both sides, because log is the inverse of exponentials. So if I have y equals a to the power of x and I want to make x a subject, x becomes the logarithm of y. The base, you'll notice, of course, stays the same. If the exponential is base a, then the logarithm is also base a. E is a very important base that we'll come to know. It's known as the natural base, and so that's why log base e is known as the natural logarithm. And so it's log base e, also noted as just simply ln. I think that comes from the French, because they say things backwards. You know? No, yeah, logarithm naturel. So I think that's where they get the ln from. So that button on your calculator, which you probably thought was the in button, is not actually the in button, it's actually the natural logarithm button. So base e. These days, if you just write log y down, or you see just log y, and no base is written, then we assume it to be the natural logarithm. Used to be we assumed it was base 10, which was known as the common logarithm. And that's because we used to do everything in base 10. But now, with the advent of calculators, base 10 is not as important anymore, so we assume it's the natural logarithm we're talking about when we have so base e is our natural logarithm. Okay, so the graph, what does it look like? It looks very much like an exponential curve, but the x and y's have swapped around. So instead of going asymptotic to the x-axis, it goes asymptotic to the y-axis. Instead of having a y-intercept of 1, it will always have an x-intercept of 1. And this would be the log graph for a base that is greater than 1. If the base was in between 0 and 1, then it would flip in the x-axis, so we'd get the blue curve. Just like with our exponential curve, if you had a base greater than 1, it would be the one we normally see, but if the base was between 0 and 1, it would reflect in the y-axis. You don't have bases of logarithms that are negative. Same as when we write our exponentials, we don't have bases that are negative. And base 1 really is meaningless, same as in an index. Base 1 is meaningless because, of course, 1 to the power of anything is 1. Okay. Domain, all the sorts of things we like to define functions with. Well, we can see from the graph, it doesn't matter which base we're talking about. The domain is greater than 0. And the range is all real y. There are no gaps in the graph whatsoever, no breaks. It is a continuous graph. As far as odd and even functions go, it's neither, of course. There is no reflection symmetry or rotational symmetry in that graph. All right, it's important we have some log laws. Otherwise, the log police will come along and put you in log jail, which would be easy to get out of, really. All you'd need would be a saw. Anyway, now, they're very similar to the index laws, of course, because of that relationship. You remember in index laws, we said when we multiply, we add the powers. So log laws is kind of like the reverse of that. When we're adding logs, we multiply the, well, for want of a better word, power, but the m and the n in this case. So mn. And so similarly, with indices, we said when we divide, we subtract the powers. So here, when we subtract logs, we divide. It's also very similar to what we saw in complex numbers with arguments, you'll notice. Yeah. So when we were multiplying, we added the arguments and so on. M to the power n, well, we've seen this one when we've been solving exponential equations. This is the one that allows us to bring the power to the front. And that's quite handy when we're solving those exponential equations. Index law, anything to the power of 0 is 1. So the reverse of that is the log of 1 is always equal to 0. And if you have log a base a, that's going to be equal to 1. Because the way you read your log, the base to the answer should give me what I'm logging. That's the relationship, if you like, if you was to turn it into index form. So a to the power of 1 is a. So log a base a will always be 1. And because they are opposites, or inverses more correctly, they will cancel. So if you have a log in the power, if the base is the same, they will cancel out. So a to the power of log base a will just be x. The inverses cancel each other out. This is what's known as the change of base law. And this is useful, I suppose, if you're trying to work out a log to an unusual base. I mean, your calculator can't physically have every possible base log. It only has the natural logarithm and the common logarithm, so base e and base 10. But if you wanted to do something base 2, you could convert it to either of those using this idea. So log base a, I would change it to 109, let's just call it base b. And so it would be the log base b, but we divide it by the log of the old base, or the original base that we were working with, and that should give us our answer. Okay, a couple of quick little questions here. So, if I see x is log 125 base 5, in my head, if I want to read this, I'm saying 5 to the power of the answer should give me what I'm logging. So we're saying 5 to the power of x is 125. So a lot of these you can just look at and read off the answer. 5 to the power of what is 125? Okay. But of course, if you don't see that straight away, then we undo the logarithm. And just like any equation, how do you undo it? You do the inverse. You want to get rid of the multiplication, you do division. You want to get rid of the addition, you do subtraction. So if I want to get rid of the log, I exponentialize, if there is such a word, both sides. But the base has got to stay the same, of course. So the left-hand side becomes 5 to the power of x. We've just gotten rid of the log, so it becomes 125. And so, in fact, it is the exact same question we were just asking ourselves anyway. 5 to the power of what is 125, so x is 3. So this one, when I look at it, I'm saying x to the power of 3 should be 343. But again, if you don't see that straight away, you can think of it as, okay, let's exponentialize both sides. X is the base, so we'll end up with x cubed is 343. Cube root of 343 is 7. Evaluate. Really the same question, just a different way of asking it. They haven't just written x equals. So we're saying 4 to the power of what is 16. So I could do it using log laws, of course, if I forgot that. So I could rewrite 16 as 4 squared. And then I can use my log law to bring the power to the front, and I get 2 log 4 base 4. But we said log of anything to its own base is 1, so that becomes 2. So if you don't see it straight away, remember we're looking at it, the base to the power of what would give me 16, which of course, if you see that, it's very quick, bang off, 4 squared 16, so the answer's 2. You could work it out using the log laws. 6 to the power of 2 log 3 base 6. Now the bases are the same, but at this stage they can't cancel. Because I don't have 6 to the power of log, I've got 6 to the power of 2 log. So I need to use my log law and bring the 2, this time, inside the logarithm, so it becomes 3 squared. Now the log and the 6 to the power of will cancel, And so the answer is just 3 squared, which is 9. Okay, log 16 base 2 plus log 8 base 2. I could do it one of two ways, I suppose. I could look at log 2 and say, well, 2 to the power of what's 16, 2 to the power of what's 8, add them together. Or I could use my log law that says when I'm adding, that's the same as multiplying, and so I get a single log, because the bases are the same, so I can do that. Now I'm saying 2 to the power of what's 128. Big number. 7. 2 to the power of 7 is 128. So 7's our answer there. Okay. This one, not quite as easy because, of course, 10 to the power of what is 125? Oh, it's not a nice, neat answer. So I'm going to have to use the log laws to combine these all together. Remember, plus means multiply, minus means divide. So this is the same as finding the log of 125 times 32 divided by 4. Turns out to be 1,000. So now we're saying, well, 10 to the power of what is 1,000? And that is, of course, 10 to the power of 3 is 1,000. Be careful, very tempting to say this is the log of 4, but no, that's not the rule. We can't just divide like so. So these are separate. What I can do here is change this into one log using that change of base in reverse. See, notice the bases are the same. So I could rewrite that as log 8 base 2. Because had I gone the other way, I could have said, let's convert this to base 7, and it would have been log of 8 divided by log of the old base. So I can do division, if the bases are the same, that way, by combining it into 1, and it'll become log 8 of the base of the bottom, base 2. So now we're saying 2 to the power of what is equal to 8? Well, of course, 2 cubed is 8. Ooh, log of the square root of 1/8 to the base 2. 2 to the power of what is the square root of 1/8? Okay, I'm going to play around with it a bit, make it a bit easier. 1/8 is power of a half, so I can bring that to the front. Using the log law, bring the power to the front. So now I have 1/2 log of 1/8 base 2. Well, that'll be -3, because 2 to the power of 3 is 8, so therefore 2 to the power of -3 must be 1/8. So we have -3 on 2 as a final answer. Okay, an exponential equation. This is where our logs really, we've used them for these sort of things so far. So we see it in the power. Well, let's log both sides, although I didn't do that. Okay. I rewrote both as 3 to the power of something because, of course, didn't notice that. Look at that. 1 on 27 can be rewritten as 3 to the power of something. So because I've got them both as 3 to the power of something, I can then say, well, the powers must be equal. So x is -2. That's great if you do notice that, which obviously I didn't originally. However, something like that we can't do, because how do you write 9 as 2 to the power of something? That's where our logs come in useful, because using our log laws, the power can now come to the front, so I can isolate the x by now dividing by log 2. So log 9 divided by log 2, it does not matter which button you press on your calculator as long as it's the same one. So use the same for both. And to 2 decimal places, that one's 3.17. And so if you don't believe me, go 2 to the power of 3.17. We won't get 9 exactly, of course, because I've approximated. Should be very close to 9, though. There we go.